right, 16.2. Some acid-base theories. So there are a couple of different theories that exist about how acids work and how they work together. And we're going to have to discuss them, and we're going to have to kind of look at them and be aware of them. So the first one is the Arrhenius acid, and this is the one we're already pretty familiar with, or hopefully are pretty familiar with. The Arrhenius theory states that acids are compounds that release H plus ions in an aqueous solution. So again, that's what we looked at yesterday and in the last unit as well. Now, not everything was just going to drop a hydrogen. Only a very polar bond will ionize. But, kind of a hint there may be multiple ionizable bonds, or H's. So, for example, hydrocarbons tend not to ionize. The electronegativities, remember we know the polarity of a bond based on the difference of electronegativities. The difference of electronegativity between a carbon and a hydrogen is very small, something like 0.3 or 0.4, not technically polar. So H's tend not to come off of carbons. Generally, to be an acid, the H has to come off of a stronger nitrogen, oxygen, fluorine, chlorine, bromine, the elements more to the upper right of the periodic table in order for them to be considered ionizable. So again, there might be multiple ionizable H's. So some terms to go along with that. Monoprotic, so one. Protic means proton. One proton acids have only one ionizable H. The examples there, hydrogen chloride, hydrogen bromide, or hydrochloric acid, hydrobromic acid. There's only one H. Once that H comes off, the process is over. But you might also have diprotic acids, which have two. So di for two protons that can come off. Some examples there could be H2SO4. Sulfuric acid. Notice the two H's. Each of them can come off in a solution of water. I'm not saying they both will, but they both can. That makes this a diprotic acid. Or carbonic acid. This is the polyatomic ion carbonate. Has two H's, so it is a diprotic acid. Either of those H's could come off of that ion. And then there are even a few triprotic acids. Tri meaning three, and so they have three protons or three H pluses that can come off in a solution. Phosphoric acid is my example there, H3PO4. All right, we have to introduce a little bit of organic chemistry, even though we don't get to that until the very end of the year. But introducing it now will help us kind of recognize some of the names we'll see during acids, and it'll give us a preview of what to expect when we get to organic at the end of the year. Organic acids have only one ionizable H, so they're monoprotic acids. We also call them carboxylic acids. You've perhaps looked at them in biology or the PBS courses that you're in. Carboxylic acids have a COOH functional group. C that is double bonded to an O and single bonded to an OH. And that H is ionizable. It can come off. So naming organic acids, how can you name them? How can you tell that they're there? Some practice. We want to count the number of carbons that we have. So we remember from first semester, 1 is meth, 2 is eth, 3 is prop. We go 4 is bute, 5 is pent, 6 is hex. So hopefully you remember these, or if not, go back and perhaps look at the notes from organic chemistry during first semester. But in order to signify we're not just working with a chain of carbons, we drop the E at the end. So notice that they all have an E, A and E, A and E, A and E. We drop the E, and we add oic acid. So for example, CH3, CH2, COOH, we count the number of carbons, 1, 2, 3. We would normally call this propane, But we're going to drop that E because we see this OOH here. And we're going to call it propanoic acid. Prop because there's 3 carbons. Anoic because we have this organic acid here that H can come off. So propanoic acid. How would you draw pentanoic acid? Well, again, we should remember pent means 5. Again, we see that oic acid there. Tells us we have a COOH at the end. So 4 carbons and a COOH at the end. Make sure all of your carbons are filled up with hydrogens. So the carbon at the end has a CH3. Carbon in the middles have CH2. And we get to that last carbon, that 5th carbon, and he's got that OOH, pentanoic acid. Again, not all H's are ionizable. You have to have a polar bond. These H's attached to this C, they won't come off. That's not a polar bond. Only the H on the end here will come off, and it'll leave you with COO negative because that H plus went off. All right, so here's some examples of what we do with Arrhenius acids. So show the stepwise ionization of sulfurous acid. So stepwise means show each acid coming off or each H coming off. They come off one at a time. And again, oftentimes they won't completely come off. You might end up here with only one H coming off quite often. We'll talk about that more later when we get to buffer solutions. But H2SO3, one hydrogen ion comes off. We're left with HSO3 negative. Now, again, stepwise, we're going all the way down to the bare minimum. That second H can come off, so that's our second step. Again, when we talk about the mathematics behind it, though, we have to break it into 2 different steps. This first H is going to come off a lot more readily. H2SO3 is a much stronger acid than HSO3 negative. Draw the structure and show the ionization of pentanoic acid. All right, well, we've already drawn pentanoic. It has 5 carbons. We get that OOH. Hey, here's that double bonded O and the OH. So here's what it actually looks like. It's not really an OOH, though if you drew that, you're fine. And when that acid comes off, when that H plus comes off, you're left, you still got the double bond to O, but now you've got that negative charge and an H plus by itself. All right, Arrhenius bases. Again, we've already kind of talked about the Arrhenius theory. Arrhenius says that compounds that release OH negative are, in aqueous solutions, are bases. So this includes, obviously, all hydroxides. Sodium hydroxide, potassium hydroxide, ammonium hydroxide. They're all going to dissolve and produce hydroxides, OH negatives, in water. But there are other types of bases as well. So just because it's not donating an OH negative, just because it's not giving an OH negative, doesn't mean it can't create OH negatives when it goes into water. All it needs to do is peel an H plus off of a water molecule, and you're left with a hydroxide ion. So, organic bases, and we worked with organic acids on the last slide. Now we're taking a look at organic bases. These are generally called amines. Have an NH2 functional group. That NH2 is really likely to go out and grab a third hydrogen, make it NH3+, and where to get that hydrogen? Well, from water, which leaves the water molecule as a hydroxide ion. So, making sure we can name our organic bases. Kind of the same idea as the organic acids, but instead of adding the oic acid, we're going to drop the entire A and E, so not just the E, and we're going to add ilamine. So for example, CH3 and H2, just one carbon. He's bonded to this NH2. One carbon means meth, so we call it methylamine. How about the formula for butylamine? Okay. But means 4, so we're going to have 4 carbons. Again, the one on the end gets 3 hydrogens. All of them in the middle have 2. And then on the end of this guy, we're going to stick that NH2. There's our butylamine. That amine tells us we have this NH2 sticking off the end. So show the ionization of barium hydroxide. All right, well, if we put barium hydroxide, don't forget, barium is an alkaline earth metal, so it has a positive 2 charge, and it'll have 2 hydroxides. When it goes into water, it drops both of them. Now, we don't do a stepwise formation like we did with the acids, because when barium hydroxide dissolves, it isn't left with a halfway product. It goes from BaOH2 to Ba2+ and 2OH negatives. There is no stopping point in the middle. How about the structure and the ionization of butylamine? Okay, butyl means 4. We did that guy up here. Here's the amine part. And again, the idea is he has no OH to give, but he can pull a hydrogen off of a water. And when he does, that leaves us with a hydroxide ion. So we now have a base. All right, so that's Arrhenius acids and bases. There is a second theory of acids and bases, and that's the Bronsted-Lowry theory. Bronsted and Lowry kind of have the acids and bases working together. So water doesn't necessarily have to be present. I'm not saying it won't always, but it doesn't necessarily have to be present other than you're going to be working with a solution in water. But we're not necessarily talking about an increase in H+ in water. We're not necessarily talking about an increase of OH- in water, though you'll see how those concepts come back into play once you get more familiar with this theory. So, Bronsted and Lowry suggest that acids are hydrogen ion donors. Bases are hydrogen ion acceptors. So when an acid loses that H+, it has to go somewhere. It goes to the base, and we call the species that remains, so the acid that had lost the H+, is now what we call a conjugate base. So an acid becomes a conjugate base. Again, the idea is, once an acid's given up his H+, he could now take one back. That makes him a base. When a base takes an H+, remember he's an acceptor, that species, the result of the base with an H+, is now called a conjugate acid. He now has an H+ that he could be giving away. So, reversible reactions from 2 chapters ago, all of these reactions are, to some extent, reversible. All right, so here's some Bronsted-Lowry theory in action. Here we have ammonia, it's dissolved, and water. And what happens to the NH3 from the left to the right? He went from NH3 to NH4+. That makes him a base. He has accepted an H+. Water, here's water, H2O, he's a liquid. He went from H2O to OH negative. Again, my theory, what I like to do is stay away from the H's, look for the non-hydrogen atom. So this is a non-hydrogen atom, oxygen. He goes from 2 H's to just 1 H. So he donated or gave away an H+. That makes him an acid. Cool, we get to the other side. And again, these are potentially reversible reactions. What if we went back the other direction? The NH4+ would now be giving away an H. He has 4 on this side. If he moves in the opposite direction, now he has 3. So that makes him an acid. Although it's a weak acid, we call it a conjugate acid. And OH negative goes from OH negative to H2O. That makes him a conjugate base. He is accepting a proton this time. He's taking that H+. Again, he's stronger as an acid in the H2O form, but once he gets there, he's now a conjugate base. Take a look at another one. So here we have hydrochloric acid. All right, that one's pretty easy. We can name that an acid. Water, H2O. We take a look at what happens to O from the left to the right, from the reactants to the products. He starts with 2 hydrogens. He ends with 3 hydrogens. He gained a hydrogen. So he accepted a hydrogen. In this particular circumstance, water is a base. We come over to the other side. H3O plus is now our conjugate acid. He has the H to give back to Cl if you moved in the opposite direction. And chloride ion is now the conjugate base. If you move back in the opposite direction, the chloride ion would be accepting a proton. That makes him a base, but we call him a conjugate base because he's certainly stronger as an acid. So there are a lot of what we call amphoteric substances. These are, so ampho means both, like an amphibian is both water and land. So that makes this so ampho means both. I'm not sure exactly what teric means, but amphoteric means it can act as both an acid or a base. In this case, we see an example of water acting as an acid and then as a base. So water is amphoteric. So there are quite a few substances out there that can act as both an acid or a base. They're known as amphoteric. All right, when we say strong acids and bases, make sure you recognize we're not necessarily talking about a high or low pH. The strength of an acid simply refers to the fact that it completely ionizes in water. Weak acids, on the other hand, it's not to say that they have a really high pH, they only partially ionize in an aqueous solution. So it really has no difference, no matter about what their pH is. pH has no bearing on a strong acid versus a weak acid. So make sure you think that one through. Here we have a strong acid. Notice we have a black and white dots, and they all dissolve. Here we have a weaker acid. Only about half of them dissolved. That's what makes it a strong or a weak acid. The concentration doesn't really come into play. Make sure you memorize this list of strong acids and strong bases. You are expected to know them, recognize them, and use them. So memorize these strong acids and strong bases as we go forward. Kind of throwing a couple more terms at you. Electrolytes in general are compounds which conduct electricity when dissolved in water. So they carry a charge when they're dissolved in water. So here we have sodium chloride. We have positive and negative charges. A very bright shining light bulb. Definitely an electrolyte. Here we have hydrogen fluoride or hydrofluoric acid. Does not completely dissolve. So that makes him a weak electrolyte. The light bulb is on, but it certainly is not as bright as it was over here. And then over here we have our sugar molecule. Does not dissolve at all. No electricity is passed. The light bulb remains off. That's a non-electrolyte. So anything that dissolves in water, we call it aqueous. We use the back of our periodic tables, our solubility rules. These are strong electrolytes. Weak electrolytes are generally not soluble, as they don't, at least not 100%, dissolve into their ions. Homework for this evening.